Today we are going to be answering the question, how many of these molecules are polar? Here we have sulfur trioxide, oxygen difluoride, beryllium chloride, carbon tetrafluoride, and ozone. So the steps necessary to solve the problem is for each individual molecule, we're going to draw the Lewis structure, identify the bond dipoles using the differences in electronegatives, and identify the net molecular dipoles based on molecular geometries. So our first molecule is sulfur trioxide. So first thing in order to draw the Lewis structure is to determine the number of valence electrons. Sulfur has 6, and each oxygen atom also has 6, which will yield us 24 valence electrons. So we're first going to start by drawing this out. Have a single bond and a double bond to satisfy the sulfur, and then we're going to subtract the amount of valence electrons we just used for those bonds. So remember that it's 2 electrons per bond. We have 4 bonds, that's 8 electrons, which is going to leave us with 16 left. So now we're going to fill in the octets for all the oxygen atoms, and that's 2, 4, 6, 8, 10, 12, 14, 16. Now we have 0 left. So that's what we're looking for. Notice too that this molecule exhibits resonance, to where these sets of non-bonding electrons could be used to make a double bond, since oxygen always wants to make 2 bonds to have a 0 formal charge. So that means like you could have a different Lewis structure where it would look something like this, or that. So the final Lewis structure is going to, the hybrid resonance hybrid Lewis structure is going to look like this. Okay, so this is our final Lewis structure, and now we're going to use the differences and electronegativity to determine which way the dipoles will be corrected. So oxygen has an electronegativity of 3.5, whereas sulfur has an electronegativity of 2.5, making oxygen the more electronegative. This means that the dipoles are going to be pointed towards oxygen, which has a partial negative charge because it is more electronegative in this molecule. Therefore, the oxygens will have a partial negative charge and sulfur will have a partial positive charge. So now that we have this, we're going to look at the molecular geometry. So since the central atom, sulfur, has 1, 2, 3 domains seen by these 3 sets of bonds, keep in mind too that even if this is a single, double, triple, quadruple bond, that's still considered one domain. So here is our molecule and its geometry, and that is going to be a trigonal planar geometry. And we're going to draw the dipoles. Okay, and here are our partial charges. All right, so this is what the final product is going to look like. So we're going to use this to determine if there is a net dipole or if there's not a net dipole. So the way to do that is, first you look at the central atom, and then if if all the domains are the same, then the dipoles do in fact cancel. And here, all the domains are the same. It's all the same atom, and there's no sets of non-bonding electrons. So, because all the domains are the same on the central atom, the bond dipoles cancel, and therefore there's no net molecular dipole, which makes this molecule non-polar. So, next we have oxygen difluoride. So, we find the number of valence electrons. Fluoride has 7, which yields 20 valence electrons. And then we go to draw our Lewis structure. And so we've just used 4 electrons. We have 16 left over. So let's go fill the octets of the fluoride. And then we still have 4 valence electrons left over because we only used 2, 4, 6, 8, 10, 12 from this 16. And we use those 4 to then now fill out the valence electrons for oxygen. So, now we have this, and now we want to look at the electronegativity of this Lewis structure. And there's no resonance because oxygen does have a formal charge of 0, as well as the fluoride atoms, because oxygen has 2 bonds and each fluoride has 1. So there's no reason for this to have resonance since it is already the best Lewis structure it could be. So now we look at the electronegativity, and we know that fluoride has an electronegativity of 4, whereas oxygen has an electronegativity of 3.5, meaning that fluoride will in fact be the fluorine, by the way, will be the more electronegative atom, meaning that the fluorine will have the partial negative charges, whereas oxygen will have the partial positive charge. So now that we know this, now we're going to go to the geometry. So the electron domain geometry for this will look something like this, since electron domain geometry includes unpaired electrons as well as paired electrons. However, in order to determine the net molecular dipole, we want to have the molecular geometry. So the molecular geometry will look something like this, since it does not include unpaired electrons. But because we do know the existence of these unpaired electrons, we know that this molecular geometry will in fact be bent. So oxygen will have the partial positive charge, whereas the fluorine atoms will have the partial negative charges. So the dipoles will be directed this way. And then the net dipole, so because the central atom, because all the domains on the central atom are actually not the same, because the sets of unpaired electrons, in addition to the fact that the net molecular dipole goes downward and does not cancel, then this molecule does in fact have a net dipole and is polar. All right, so next we have beryllium chloride. So we know that beryllium has 2 valence electrons and chloride has 7. Oop, sorry. So this will result in us having 16 valence electrons. So first step is we draw the Lewis structure and then our single bonds. So now we have 12 electrons left. So now we want to satisfy the octets for the chlorine atoms. Now you may notice that beryllium does not have a full octet. Well, that's okay because beryllium is one of the atoms that does not need a full octet and can violate the octet rule. So this is in fact our best possible Lewis structure. So now we want to look to see which one is more electronegative. We know that chlorine has an electronegativity of 3.0 and that beryllium has an electronegativity of 2.0, making this have the partial negative charge and beryllium have the partial positive charge, as well as the dipoles pointing towards the chlorine atoms. So now that we know this, we can now skip to the geometry. So this is going to have a linear geometry, both electron domain and molecular, because there are no sets of unpaired electrons which would make it to be bent, and there are 2 domains. So since we know this and we know that chlorine has the partial negative charge and beryllium has the partial positive charge and the dipoles go this way, so since the central atom has the same domains, then we know that the bond dipoles cancel, which result in us having no net molecular dipole, making this molecule non-polar. Now we have carbon tetrafluoride. So we know there's 4 valence electrons in carbon and then 7 in each chlorine atom, which will result in 32 valence electrons. So now we can draw our Lewis structure. Just going to look something like this. Carbon likes to have 4 bonds, which will give it a formal charge of 0, and chlorine likes to have 1 bond. So all our formal charges here are 0. So this is the best possible, well, as of right now, this is the best possible Lewis structure you can have. So, but now we need to fill the octets of chlorine. So we just used 8 electrons, so we're going to have 24 electrons left over. So let's go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we have 0 left. So we have no electrons left over. Everything satisfies the octet rule, and all the formal charges are 0. So this is the best Lewis structure we can have. So now we want to see which ones are more electronegative, which atoms. So we know that chlorine has an electronegativity of 3, whereas carbon has an electronegativity of 2.5, meaning all the chlorine atoms are going to have a partial negative charge, and carbon is going to have the partial positive charge. This also means that the dipoles are going to go towards the chlorine atoms. Once again, in case you forgot, the dipoles point towards the more electronegative atom, and this cross-looking figure means that is the positive end. Now that we have this, now we're going to go to the geometry. So, we know there are 4 domains on the central atom, so that means our geometry is in fact tetrahedral. And since there are no unpaired sets of electrons, both the electron domain geometry and the molecular geometry will be tetrahedral. And then we now are going to draw the dipoles again. As well as our partial negative charges, so as not to forget, and our partial positive charge on carbon. So, since the central atom, carbon, has 4 identical domains, then the bond dipoles will in fact cancel, meaning that there is no net molecular dipole, which would make this molecule non-polar. Just to review, if the central atom has 4 identical domains, then there will be no net dipole and it will be non-polar. Okay. Lastly, we now have the molecule O3, also known as ozone. So we know that there are 6 valence electrons for each oxygen atom, leaving us with 18 valence electrons. If you write out the O3 molecule, it will look something like, first you're going to start with 3 bonds. So now we're going to have 6 electrons used, which will leave us with 12. So now we're going to satisfy these octets, 2, 4, 6, 8, 10, 12. Now all the octets of each oxygen atom are satisfied. However, this molecule exhibits resonance because this set of unpaired electrons can come, yes, this set of unpaired electrons can come here to form this bond. And then this bond would come back to here. So in other words, the other Lewis structure could look something like this. So our hybrid resonance structure will look like this. So this is our best possible Lewis structure. So now we're going to look for the electronegativity, and all 3 of these have the same electronegativity. So we're not even going to bother about drawing the dipoles. Instead, what we're going to do is look at the molecular geometry as well as the electron domain geometry. So the central atom has 3 domains, one of them a non-bonding pair of electrons. So because it has 3 domains, we know that the electron domain will in fact be trigonal planar. Now, the molecular geometry will be bent because we know that there is this set of non-bonding electrons that pushes these 2 bonds downward, making the angle slightly smaller. So because oxygen has 3 domains, this first one not being identical to these two, we know. So because the central atom has three domains, all 3 of those domains are not equivalent. This is not equivalent to 2 or 3 because it's a set of non-bonding electrons. It is not a bond. So because they are not equivalent, there is in fact a net dipole, making this molecule polar. So just to recap, if the central atom has a domain that is not equivalent to the rest of them, then it is in fact polar. So before we recover the final answer, just some common mistakes while working out these problems. The first would be drawing an improper Lewis structure, and that could result from miscalculating the number of valence electrons or not recognizing resonance. Another big common mistake is incorrectly determining the correct geometry. This could result from just not being able, from miscounting the number of domains or not realizing the molecular geometry. And then the third would be incorrectly identifying which atom's more electronegative. So even if you do not have the numerical values for each atom's electronegativity, you do have the periodic table, and you know that the periodic table trend for electronegativity goes like this up to fluorine, which is the most electronegative. And then given that there are a few exceptions, such as the fact that chlorine and nitrogen are equal, even though nitrogen's 2 away from fluorine and chlorine's only 1 away. Also, another important exception to remember is that hydrogen is in fact more electronegative than boron. So if you know that the trend goes to the right and up, that chlorine and nitrogen are equivalent, and that hydrogen is more electronegative than boron, then you should be able to easily determine which atoms are more electronegative. So back to the original question. How many of these molecules are polar? Well, we determined that sulfur trioxide was in fact nonpolar. We found out that oxygen difluoride was polar, that beryllium chloride was in fact nonpolar, that carbon tetrafluoride was not polar, and that the ozone was polar. So the answer to the question is there are 2 molecules that are polar.